We are back with Stephen Williams of Southern Technical College as he continues with Chapter 7, this time discussing solid-state relays.
Now, one way to think of solid state is they're solid. There's no movable parts. What are they? When you get into electronics, one of the first things you learn about electronics is they're made with what they call semiconductors. In other words, it's not like copper that's a conductor or silver that's a conductor, and it's not like, for example, plastic, which might be considered a insulator, okay? But it's a semiconductor. So whenever you're talking electronics, you're generally talking semiconductor materials, a lot of times silicon, and they make other kinds. I am not a electronics whiz, but I will tell you that as you get into it, you're going to find now that there's no moving parts. So it has some advantages. It's not going to wear out. Can it burn up? Yeah. In fact, one of the advantages that a mechanical relay has over a solid state relay is the fact that if you get hit with a surge, chances are there's going to be no damage to a electromechanical relay because they can handle a little bit of surge. All right, electronics cannot. They're designed to handle a very specific voltage, and if it has a surge of voltage coming into it, literally it will fry it.
Pop.
So that is a failure mechanism that comes along with the advantages that they provide. All right, so with that in mind, let's look at a solid state relay and see how they work. Let's turn this on and get into our presentation. How they operate is, it's an electronic switch, okay? All right, so electronic switch, all right? Well, let's get right into some of the diagrams you have here, right here. All right, so I have, just like in the electromechanical relay, I can have different power sources on both the input and the output. In this case, I have DC. Typically, DC is used with electronics, and that's being shown here, feeding the input. Okay, so the thing that's missing here is the fact that there's not a switch, all right? But let's suppose there's a switch in here and the switch closes. When the switch closes, you have a complete circuit. All right, when that circuit is closed, you have a flow of electricity through this diode, okay? It's a light emitting diode, but once it starts flowing, it'll only flow in one direction, all right? Which would be positive on this side through to negative. It will not backfeed the opposite direction. In this case, since it's light emitting, it emits light. That's picked up by a phototransistor. Okay, that's a transistor that's sensitive to light. Okay, and is therefore activated by the fact that the LED just put out light. When that triggers the LED, it also triggers the phototransistor. Now, transistors in general are amplifiers. Okay. And I'm not going to go into how they work and all that because it's way beyond the scope of what we're trying to get into here. However, think of it as an amplifier that now, once I've got a signal that's big enough, all right, because it'll filter out noise. So let's suppose I've got a little bit of noise in the circuit. It'll filter that out because the trigger circuit is saying, if it's not this big, I'm not going to do anything. But as soon as it gets that big, boom, it triggers. Now, once it triggers, now you have the flow of current, all right? And it's coming over here to a triax. And a triax, think of a triax as a valve that has a, let's call it a solenoid valve, all right? And when the trigger circuit triggers, all right, in this case, the triac will start flowing. In other words, you just took that solenoid valve and energized it, and when I energized it, I took it from a closed valve to an open valve. Now it's flowing. Now that it's flowing, it can feed a load, okay? And if it's supplied from AC, it'll feed an AC load. If it's supplied by DC, it'll feed a DC load. But typically, they're independently fed, okay? Almost always independently fed. They're not fed internal to the relay itself, all right? This power that's going in there, again, has to be closed via a switch of some kind before the LED is going to turn on. Once it's, and that provides the power that the LED knows to operate, okay? And so the electronics then is fed that way. And on the load side, it's fed whatever way the load is fed. All right, you can have it as small as, you can see the chip there on the bottom, okay? And they don't necessarily have to be big. I've seen some that have been, like you say, ice cube size, because that's all it takes to put some electronics inside there. Really, it depends upon what kind of load it has to handle. If it is actually flowing through that triac has a load limit, all right? So sometimes you need to have a secondary device, like maybe a electromechanical relay pickup via the output of that, to be able to power a load that's heavier than what this can handle, all right? But again, we're not here to discuss that. The point is, all of this that's part of the relay is all semiconductor material, okay? How they put it together in there, magic, okay? And guess what? If it doesn't work, you throw it out and get a new one, because they're not all that expensive. Okay, and there's different kinds. Like I say here, you've got a photodetector that goes into the power transistor. Okay, there's a lot of different kinds, but again, you've got something that's triggering it. Now this LED here is acting as a buffer between input and output, so you actually have independent circuits there. And the only thing that's going between the two circuits, the input and the output, in this case, is light. All right, so it's not going to pass. If I have a short circuit on the input or the output, it won't pass it through. All right, so it's inherently a little bit safer, but it heats up with the power that's going through it, so it does produce probably a little more load than the mechanical relay would, a little more heat, I should say, because the small contacts on a mechanical relay are very tiny, and there's very little to heat up there. Yet the whole surface of the semiconductor material is part of a circuit that's heating up as current's flowing through it in both directions. LED doesn't draw a lot, but that load, well, whatever it's designed to handle. Okay, moving on. Specifications, okay. I don't care. All right, if you need to buy one, you buy one to replace what you've already got. Okay, when multiple poles are required, a common solution is to wire several relays in parallel to provide an equivalent function, multi-pole magnetic relays. Okay, so I've got a bunch of little tiny relays, and believe me, these are fairly tiny, and you can wire them up in parallel so that when one energizes, they all energize. And that's essentially what they're doing here, is multiplying them. Okay, here's the same thing that we're talking about there, 3 pole solid-state relays are used to switch current in three-phase loads. Okay, think of this as, three-phase loads. Normally, you're not dealing with light loads, okay? And when you're trying to handle more than a light load, you're not probably going to use tiny pieces of semiconductor material. For example, you're probably not going to use the transistor. You're probably going to use what they call like a silicon control rectifier. All right. Now, what that is, it's kind of like the triac, in as much as the triac has a gate going into it that turns it on and off, but the silicon control rectifier is a much more, they're built much bigger. They can handle the heavier load that goes through them. But when you start getting into those heavy loads, you're also dealing with the necessity to keep them cool. Okay, so you need to keep them, in other words, they might have a heat sink as part of the enclosure so that you can have airflow around them. The standard configuration, 2-wire control. Okay, you have a control device initiating it, just like we mentioned on the other part. Okay, and then you've got something that's causing the starter, okay, to pick up. Internal to it, it's probably not just a tiny contact. All right, you can look at, there's a number of different ways. Okay, again, using an SCR, what do they say here? The start button press, current flows through the gate, which triggers the anode to cathode section of the SCR control relay circuit into conduction. Literally, it will start flowing through the semiconductor at that point, current, all right? And because it's not intended as a conductor, even though it is, it heats up more than a conductor would. In other words, I can upsize my conductors, make it a larger size, lower resistance, get a lower heat buildup, okay? But you can't really do that with semiconductor because it's not conducting in quite the same way as a conductor would transmit electricity. All right, it's different. But again, way beyond what I want to get into here. All right, switching methods. Zero switching, inductive, capacitive. Interesting, read through it in the book. I'm not testing on that. Okay, it's way beyond what I think you need to know at this point. The big thing I want you to get out of the electronic relays is the fact that there are no moving parts, that they do produce heat, that they are sensitive to surges. They're quicker in the switching action. I mean, it's instantaneous. You don't have to worry about a contact hanging up or a coil hanging up. It does it right now, as long as the relay is not burned out. So, I mean, you can look at all this stuff, and it's interesting. Again, this is probably the best part of it here. The pros and the cons, solid-state relay. The pros, more reliable, has a longer life because it is no moving parts. Compatible with transistors and IC circuits, does not generate as much electromagnetic interference. Very true. Okay. Sorry?
Please stand by.
How do we get back to part one? Okay, anyhow, we pretty much already talked about the pros and the cons anyhow, so at this point I'm going to end this. And we'll move into section 3, which I believe is going to be talking about timing relays. So with that, let me get the right PowerPoint up here for timing relays, and we'll start over from there.